Okay, so recently I was... You know what, this is boring, let me do something else. Hello, this is me, Simulated Gravity. This is what I look like in real life. Just trust me bro, this is 100% real footage. Now, here's the thing. Have you ever wondered why my name is Simulated Gravity? Well, it's because it sounds cool. Yeah, not very well chosen. But to be fair, when making games, you do a lot of gravity simulation. So I decided I'll actually live up to my name today and actually make a video about it. Well, I mean, if you're making a video game and you want to simulate gravity, it's pretty easy, right? I mean, like 90% of game engines have built-in gravity systems. In Unity, all you gotta do is create a game object, give it a rigid body, and check the has gravity thing or whatever it's called. And boom, we have gravity. Or do we? What if I told you that this simulation here, while it looks pretty realistic, is completely wrong? But before I tell you that, I should probably say what it actually does right. Alright, it doesn't get everything wrong. I mean, it's pretty close to what it's like to just have gravity as a human on Earth. Basically, it makes stuff go down. It does this by adding a downward force every single frame, which is basically also how gravity in real life works. So when my guy jumps, he has an upward velocity, he slows down, and then he falls back down to the ground again. Now I want you to jump in real life. No, like do it right now, like just jump. Congratulations! You know what you just did? You made a parabola. Or a parabola if you are smart at. How did you make a parabola? If you pull out your graphics calculator, if we make the x-axis our time axis, and the y-axis our altitude, then you can see that you make a parabola. And a jump in my simulation also creates a parabola shape. Now, if it's completely realistic to how it's like just having gravity on Earth, then what's the deal? Why am I saying that it's wrong? Well, while it does mimic gravity very well, physically, when it comes to physics, this is absolutely not how gravity works. I mean, what even is this? You see, in the game engine, gravity just moves you down. But in real life, down is just described as the direction gravity takes you. So, obviously, we're missing a step here. Do you know this man? You probably do. His name is Sir Isaac Newton, and he discovered gravity. Kind of a big deal. See, before he was around, people thought apples fell to the ground because they kinda just wanted to do that. But he discovered that the apples are actually being attracted to the Earth's enormous mass, like how I am attracted to your mother's enormous mass. All jokes aside, he came up with this formula, which is what we're gonna use to simulate gravity correctly. So a while back, I made this simulation. So basically, it simulates gravity. So when I create two objects, they attract each other, which is how gravity actually works. And the way I made the objects attract each other is using this formula here. So if I go into my code, you can see it's literally right there. There's the formula. So basically, I'm gonna explain what this formula does and what all the parts mean. So this formula calculates the force two objects have pulling each other. Yeah, two objects pulling each other because when two objects interact with gravity, they are actually both pulling each other with equal amounts of force. So when you fall down, you are pulling the Earth as much as the Earth is pulling you. The only thing is, the Earth is pretty heavy, and it takes a lot more force to move than you. The F in the formula stands for force. That one's pretty obvious. The G stands for gravitational constant. M1 is the mass of one object, M2 is the mass of the other object, and D is the distance between the objects. So, in conclusion, the force pulling the two objects together is equal to the gravitational constant times the mass of the first object, the mass of the second object, and then divide it all by the distance squared. Alright, first of all, what's the gravitational constant? Well, basically, it's this number. And the reason why this number isn't just written in the function is because it would look like this, which is a little long. And just to clarify, there's been some confusion on the internet. This is not the gravitational constant. This number is just the force of gravity we experience on Earth. This number here is the actual gravitational constant. What the gravitational constant is basically the scale of gravity in our universe. It's constant everywhere. Then, the mass of the first object and the mass of the second object. To explain this, let's say we have two objects. They are at a distance of 1 meter away from each other, and one weighs 2 kilograms and the other weighs 3 kilograms. This means they would be pulling at each other at a force of 6 times the gravitational constant, of course. Now, why is it 6? Well, let's imagine for a moment that instead of two spheres here, we just have 2 balls that are 1 kilogram each, and 3 balls that are 1 kilogram each. This ball here, which is highlighted red, is being attracted by all 3 of these balls. So it has a force of 3, times the gravitational constant, of course. Then this one also has a force of 3. These ones are only attracted with a force of 2 because there's only 2 on the other side. But there's 3 of them, which means that both sides add up to 6. Which is why it's mass 1 times mass 2. And of course, the smaller object will go faster because speed is equal to force divided by mass. I've basically described almost everything in this formula, so why stop there? I'm going to explain why you divide the whole thing by distance squared. The reason we divide by distance squared is that we live in a 3D universe. But before I can explain that, I'm going to explain how it works in a 2D universe. So imagine we have two objects here, and they are at a distance of 1 meter. This object here is pulling this object with gravity. Now if we draw a circle around this first object, and we give it a radius of the distance between the two objects, we can see that the circle has a circumference of 2 pi. Now here's the important thing, which is that there's only so much gravity to go around. You see, this thing generates a certain amount of gravity, and that amount of gravity needs to be spread out around this circle. If we move the second object further away, as you can see, the circle needs to be bigger to reach the second object, and the length of the circumference will be bigger, which means that it needs to be spread out more, which means that gravity will be weaker. So if our second object is 2 meters away instead of 1 meter, the circumference will be twice as big. And if it's 3 meters away, it'll be 3 times as big, and if it's 4 meters away, it'll be 4 times as big. Got it? So in 2 dimensions, the formula for gravity would just be g times m1 times m2 divided by d. But obviously we don't live in 2 dimensions, and the formula for us is different. Now why is it different? Well, if we have our 2 objects again, instead of a circle for the gravity, we have a sphere. And gravity needs to be spread around the surface area of the sphere. So, if our objects are 1 meter away from each other, the surface area of the sphere will be 4 pi. Guess what it will be when our objects are 2 meters away? If you guessed 8 pi, you'd be wrong. It's 16 pi. The surface area went up by 4 times, even though the object is only 2 times the distance away. And if we move it 3 times the distance away, The surface area of our sphere is 9 times its original size. This is because in the formula for the surface area of a sphere, it's 4 pi r squared, which is why in the third dimension you have to divide by distance squared. And now, wait, hold on, I finished the formula. Hey, that's neat. Well, now that we've finished the formula, we can go on to the simulation actually. I'll show you what I've got done already. So you can create objects, you can select between planets and stars in our solar system. You can select an object, and you can change its properties like its size, its mass, and its density, and you can rename it. And of course, objects attract each other. You know, that was the whole deal of this. So I can do things like drop the Earth into the sun and just evaporate everyone on Earth. Well, this simulation isn't actually 100% complete, which is why it hasn't been released yet, but let me know in the comments if you want me to release this thing. Now I will be honest with you, I did use a way higher gravitational constant than the one in real life, because if I used the real one, it would take a year for Earth to orbit the sun, and I'm not waiting for that. So, yeah. This means we actually have proper gravity now. Or do we? What if I told you that this simulation, while it looks realistic, is still wrong? Okay, it doesn't get everything wrong, but it is missing one very important thing. Normally, this doesn't actually affect much, and we can kinda just ignore it. But for some cases, like measuring the orbit of Mercury, it actually makes a difference. This took scientists quite a while to figure it out. I am of course talking about relativity. Do you know this man? You probably do. His name is Albert Einstein, and he discovered relativity. See, he discovered the fact that everything moves at a maximum of light speed. Nothing can go faster. And well, gravity is something, so it can't travel faster than light. Right now in my simulation, when you delete a large object, everything just immediately stops getting attracted to it. But that's not how it works. You've probably heard before that if the sun were to disappear, it would take us 8 minutes to know. Because light takes 8 minutes to travel to Earth, and that includes gravity. So Earth would just continue orbiting until the 8 minutes are over. So how exactly does gravity travel then? Well, it travels in waves. Kinda like waves in the ocean, but instead of being in water, it's in the literal space-time continuum. And these waves move, of course, at light speed. So the actual formula would go a bit more like this. And I'm not coding any of that. But luckily, I actually don't need to code anything. Because my simulation was actually a very obvious knockoff of another game this whole time. Wow, plot twist. Anyways, the game I'm very lovingly ripping off is called Universe Sandbox. Basically, it's the universe as a game. It's not really a game, it's just a sandbox, obviously. But in it, the gravity is actually 100% accurate. Well, I wouldn't say 100%, but it does use gravity waves, so that's pretty realistic. Man, why does simulating gravity have to be so difficult? You know what, actually, I have a better question. Who asked? No, like seriously, this is the next section. The answer is nobody. Nobody asked for my opinion, yet I'm here sharing it anyways. You see, I'm a game developer, and we make games. Now I don't know about you, but if you were the one releasing the next sussy spacemen game or whatever, would you be too concerned about making realistic gravity? After all, if you just give a constant downward force, and don't let the player control in the air or something, it would play basically the same as if you were to add realistic gravity. The only difference is, one solution is checking a box, and the other solution is this. And, you know, you'll probably be playing with 5 frames per second if you use realistic gravity. Now, I'm not saying there's no uses for correct gravity. After all, Universe Sandbox is a thing. And my simulation wouldn't exactly work if everything just fell to the ground. But if you were to be making something like a horror game, I don't think people would be too concerned about Mercury's orbit. So I guess it all comes down to the usage. And since most of you guys aren't physicists or making a space simulator, I wouldn't be too worried about simulating proper gravity. Wait a minute, what did I make this entire video for?